So by special request, we have a bit about intensity and waves. And the first thing that we should get right about intensity and waves is terminology. Intensity is not the same as irradiance. Intensity is defined as the power passing through a given area, but the area is perpendicular to the direction that the wave is travelling. Irradiance is again power over area, but it's the area that the power, the energy per unit time, is landing on the surface. So if we take in this little sketch, here are rays of light from the sun, here's the Earth's surface, there's its curvature, and here somewhere out in space is a 1 meter by 1 meter square section of space. So the intensity of the radiation passing through this 1 meter by 1 meter square is the power, the energy per unit time over the area, because this is perpendicular to the rays of light. However, those same rays of light, when they pass on and eventually reach the Earth's surface, well, we know the Earth's surface is curved, and consequently the area that those rays of light strike is going to be greater if we're calculating irradiance than it is if we're calculating intensity, because for intensity we're calculating the area perpendicular to the rays of light, to the energy, to the wave. Irradiance we're calculating with the area that it actually falls upon, and that area may not be A, flat, and it B, may not be perpendicular to the direction in which the rays are travelling. So because of that, we have different areas, and consequently we usually get different values for intensity versus irradiance. So unless the surface that we're using is perpendicular to the rays of light up there in that diagram, then we are normally going to get different values for the intensity and for the irradiance. And in almost all cases, the intensity will be greater than the irradiance, because the irradiance will have a larger surface area, either because it is at an angle or because it's curved. There are options for the geometry which will cause the irradiance to be larger than the intensity, but they're a bit difficult to draw out. So now getting to the waves and the intensity. Well, intensity is power over area. That's energy over area times time. But what do we use for the energy? Well, the answer is it depends on exactly what situation you're in and what circumstances you're in. And that means that we're going to need to have some nice generalizations. And the nicest generalization is that the energy transported by a wave from one place to another place is equal to k, a constant, times a squared, where a is not the area, definitely not the area this time, it is A for amplitude. So please don't get A for area confused with A for amplitude. So that's how we get that. And since we know that the intensity is proportional to the energy, and the energy is proportional to the amplitude squared, we can say that the intensity is proportional to the amplitude squared. And the obvious question is, well, where does this E equals Ka squared come from? And the answer is that whatever maths we do for whatever specific scenario we happen to be working in, it will always end up simplifying down into the form E equals Ka squared. Any situation you like, no matter how complex you want to make it, the energy of the wave, energy that the wave is transporting from point A to point B, is always going to be proportional to the amplitude of the wave squared. For example, if we look at the total energy of an object undergoing simple harmonic motion, well, add the kinetic and the potential energy together, half m omega squared, a squared minus y squared, plus a half m omega squared y squared, and we get a half m omega squared a squared. And sure enough, that's in the form E equals Ka squared, where k, in this case, is a half m omega squared. Let's try a couple of examples of what sort of thing might appear exam-wise about intensity of a wave. So we've got a wave which is getting an intensity of 5 watts per square meter. So energy wave of some kind, so it could be infrared, could be ultraviolet, whatever it is being detected, and it's being detected with an intensity of 5 watts per square metre. Obviously, I put a lot of thought into this question. Something happens, causing the amplitude of the wave to double. What's the new intensity? So, in an exam style question, there'll be some sort of waffle here that will describe something happening, the upshot of which is, oh, the amplitude of the wave has doubled. What's happened to the intensity? Well, as we know, the intensity varies as the energy varies as the amplitude squared. From that, we can deduce that the original intensity, I1, over the new intensity, I2, is equal to the original amplitude 1 squared over the new amplitude A2 squared. And since it says here that the amplitude of the wave is doubled, we can say that A2 equals 2A1. That'll come in useful for a little substitution later on. So, quick rearrangement of this tells us that the new intensity is equal to the old intensity times the square of the new amplitude divided by the square of the old amplitude. Do that substitution I mentioned earlier, and lo and behold, we end up with the new intensity is equal to 4 times the old intensity, which means that 4 times 5 is 20 watts per square metre. So, do we need to write out all of this stuff? Not with a bit of practice. What we need to remember is that the intensity is proportional to the energy is proportional to the amplitude squared. So if the amplitude doubles, then 2 squared is 4. So if the amplitude doubles, the energy quadruples, and therefore the intensity will also quadruple. Now, an example of going the other way, we've got an intensity of 54 watts per square metre being detected at some detector. There's a filter placed between the source and the detector, reduces the intensity to 6 watts per square metre. So we've got a transmitter, a detector. Initially, we're detecting 54 watts per square metre. After we put the filter in place, we're detecting only 6 watts per square metre. How does the amplitude of the wave before and after the filter compare? Well, let's look at our numbers. The original intensity is 54 watts per square metre. The new intensity is 6 watts per square metre. That means that I1 over I2 equals 9, because 54 divided by 6 is 9, at least it was the last time I checked. And that should also tell us that A1 squared over A2 squared, in other words, the old amplitude squared divided by the new amplitude squared, is also equal to 9. So we can say that A1 equals 9A2, A1 squared equals 9A2 squared, square root both sides, A1 equals 3A2. So that tells us that the original amplitude was 3 times the new amplitude. So the amplitude before the filter was 3 times greater than the amplitude after the filter. And human nature being what it is, it's almost instinctive that we try and say that the amplitude after the filter is 1/3 of what it was before the filter. But remember, no exact values. I'm writing 0.33 times, not 1/3 of, because we are in physics, not in maths, and therefore we do appropriate number of significant figures, not fractions. If you were to write this, but put 1/3 of instead of 0.33 times, it would be marked wrong because you are stating an exact value, which implies an infinite degree of accuracy, which is, of course, not a real thing, except in maths.